So Phobos and Deimos are extremely small compared to Mars. Their combined mass is only of order 10 to the minus 8 times the mass of Mars. In general, their spectra are interpreted as resembling material from the outer asteroid belt. There have been more recently claims that their spectra may show some commonalities with Mars. Notably, their orbits are very regular. They're nearly circular. They're in the same plane. Right now, the satellites are fairly well separated. Oops, sorry. Phobos is just interior to about 3 Mars radii, and Deimos is just interior to about 7. But Phobos has tidally evolved inward over time substantially, and so it's likely that when they formed, they were much closer together, with Phobos forming at, say, roughly 5 to 6 Mars radii, and Deimos forming near its current position. So the dashed vertical line here is the co-rotation radius. That's where the orbital period equals the Mars day. So interior to this line, moons tidally evolve in due to tidal interaction with Mars. Exterior, they tidally evolve out. So the origin of these objects remains very uncertain. A long-standing idea is that they're asteroids that were somehow captured intact into orbit around Mars. This is largely motivated by their spectra. They sort of look like small asteroids, but it's challenging to reconcile most capture ideas with the very regular orbits that these moons have. So it would be easy to explain their regular orbits if instead they accumulated in situ from a dissipative disk around Mars. And a natural way to form such a disk would be an impact with Mars. But we know from the many simulations of impacts that we've done that impacts that produce extremely low mass disk, something that would be comparable or even within an order of magnitude of the mass of Phobos and Deimos, those disks are very compact. Such impacts would not place material as far out as Deimos's orbit, for example. Now, if you had a compact low mass disk, it could perhaps spread due to collisional viscosity and spawn moons from its outer edge, which might be able to migrate outward due to resonant interactions with the disk. But this process has been modeled by Rosenblatt and Charnow, and what they find is that eventually all such moons spawned from a low-mass compact disk eventually tidally evolve into Mars and are lost. So if we want to try to form these objects by an impact, how could we do that? So first, I would argue that you actually need to think about a much bigger impact, because these are the types of events that could place material out as far as Deimos. Now, we know from its isotopically derived formation time that Mars finished its accretion earlier than the Earth, so it probably didn't experience the same protracted period of giant impacts that the Earth did. On the other hand, just from the rotation of Mars alone, explaining that 25-hour day implies, if you do it with a single impact, an impact by an object containing a few percent of Mars's mass. In terms of how large we would need the disk mass to be, it would have to be at least comparable to the mass of Phobos and Deimos, but it could be vastly larger because so much of the disk initial mass could be lost to inward tidal evolution onto the planet. And finally, I've emphasized that you'd have to place material out far enough to form Deimos, but you wouldn't want to create a disk whose outer edge was far beyond Deimos, because such a disk would most naturally produce a satellite exterior to Deimos that would tidally evolve outward, and in the simplest scenario, you'd expect to still see it today, and we don't see an object exterior to Deimos. So this is an SPH impact simulation. If you could go ahead and start, that'd be great, of an object containing about 3% of Mars's mass. So this is an object with roughly 30 times the mass of Ceres for scale. This is a 45-degree impact angle with an impact speed equal to the escape velocity. And this is a type of impact that will give you a Mars-like rotational day. And it also, in this case, produces a disk with 7 times 10 to the minus 4 Mars masses, much more massive than Phobos and Deimos. So we've done an initial series of these types of impact simulations, a very limited number so far. And these are results from 10 of those simulations shown in this plot for a variety of impact angles, a small range of impact velocity. What we're plotting here is an estimate for the radius of the disk once it's collisionally relaxed after it's produced by this impact. Shown here on the y-axis, plotted against the rotational day in the planet that's imparted to the planet by the impact. So in other words, the length of the day the planet has right after this collision. So what we found in this initial series of 10 simulations is that there seems to be a correlation between impacts that are consistent with Mars's day, which is indicated by the vertical dashed line here, and a disk outer edge roughly near the initial and current position of Deimos. And so this is, I would say, an encouraging result for the impact model, because it suggests that the same types of impacts you would need to explain the Martian day seem to give you, at least for our initial impacts that we've considered, a disk of the right radial scale to produce the satellites we see. But these disks are vastly more massive than Phobos and Deimos. So how could we end up with just little Phobos and Deimos as this disk evolved? So here's our concept, which is very simple. And that is that initially you have an extended disk, it's very massive, and that Phobos and Deimos are the outermost accretionary products from this disk, and eventually everything that formed from the inner parts of the disk, multiple satellites that would have been hundreds of kilometers in radius, eventually tidally evolved inwards and was destroyed as it impacted the planet. So this is a schematic simulation of this type of evolution. We're using a model we developed to describe the moon's formation after a giant impact. So we're treating the disk inside the Roche limit by a continuum model. The disk viscously spreads. The material outside the Roche limit is treated by an n-body accretion simulation. As the disk spreads, it adds material to the n-body code, and as moonlets accrete, they interact with this disk through gravitational torques. Now, this is a very schematic toy model for this particular problem, because the resolution here that we've used is very low, and this particular run did not include tidal evolution. But in the end, from this initial disk, we end up with one very crude analog to Deimos that is left just outside co-rotation, with nearly all of the disk mass contained in larger satellites, which, if we included tidal evolution, would spiral inward and be destroyed. So this is not conclusive by any means. It's really just a schematic concept idea, but these are the types of simulations that we'll be doing with much higher resolution to see if you can actually start with such a massive disk and end up only with Phobos and Deimos. So if we can get this scenario to work, what are the implications? In particular, what might be an important observable constraints that hopefully we'll be able to understand better through future missions? So if we think about the bulk compositions of the moon compared to Mars, that will, in this model, be a function of the relative contribution of the impactor versus the planet to the disk, which we should be able to determine with increased numbers of impact simulations. But if they were formed by an impact, you would expect the overall bulk composition of Phobos and Deimos to be similar to each other. And that might or might not be the case if they had formed by capture, for example. You would not expect these objects to be coherent monoliths. You'd expect them to be rubble piles. They could have some large interior fragments, but even though the rock is melted by the impact, the cooling time in the region where these moons form is very short compared to their assembly time. And as you're assembling them, the energy released is minuscule compared to that needed to remelt them. So you'd expect them to be rubble piles. And I think, perhaps interestingly, you'd expect them to generally be ice poor. And that's because the thermal velocity for molecular water vapor, and certainly for H2, at the region where Phobos and Deimos likely formed is comparable to the local escape velocity, and I see that the Mach conversion has done wonderful things to my equations. Thank you very much. So this is very different than the case in the protolunar disk. Even though things in the protolunar disk get very hot, the Earth's escape velocity is much larger than the expected thermal velocity, certainly for molecular water vapor, and over much of the disk, even for anything bigger than hydrogen. So in this case, we would probably expect them to be, in terms of their bulk compositions, ice poor. So, I present this as a concept. I'd say that the data so far, I haven't seen anything to indicate this can't work. I think that's the appropriate level of confidence at this point, or skepticism, depending on your viewpoint. A few important caveats. There have only been a very small number of low-resolution simulations done so far. The ones I've shown you, there have also been another 10 impact simulations. That's still a very small number. Reported in Citron et al. From this year. And there are additional processes that may prove important and may change the outcomes. But the basic idea here is that if you form them by an impact, then the initial Mars satellite system would have looked like this, with very large interior moons, probably a small number of them, that were eventually lost. And I'll just finish by pointing out, and this point was emphasized in the Citron et al. Paper, that there is overlap between the types of impacts that can produce the Mars day and the types of impacts that could produce the Borealis Basin. And so it may be possible to link these events, although it's not required. Thanks.
We have time for questions.
Carly Peters at Brown University. That was fascinating, Martha. You sort of alluded to it, your last few comments, some of the implications for the timing in terms of other bodies and the current Phobos and Deimos. Can you expand that a little? When could this event have occurred based on what we have now in the model you have?
So I think the impacts that are going to be most effective at reproducing Mars's spin are going to be relatively low velocity impacts by larger impactors, something an order of magnitude more massive than Ceres. Without, off the top of my head, that's going to be most probable if you have a very early event. You're going to want to do this at the end of the planet formation era, in that time. The dates I've seen for Borealis tend to be more recent than that, although I don't know how certain those are. With the Borealis impact, the basin gives you fundamentally a constraint on the impact energy, but you still have degeneracy in terms of how that's partitioned between the mass and the velocity of the impactor. So, for example, I think it's possible to do Borealis with a smaller, higher speed impact than it might be to explain the rotation and the origin of satellites. But the easiest answer is this should be the end of the planet accretion era to make it probable, hopefully.
Hi, Dan Britt, University of Central Florida. Neat idea. I spend a lot of time looking at ways of taking relatively bright matrix silicates and making them dark. And it's really hard to make them as dark as Phobos and Deimos. So I have sort of the spectroscopist's version of your aversion to capture. It's very difficult to see getting differentiated Mars material 4 or 5% reflective for the whole thing, unless you do something extraordinary.
I think you're, without doing something extraordinary, it's either necessary to conclude A, that the spectroscopy is telling you only about the upper very small percentage of mass and not necessarily the bulk composition, and or that you had an impacting object that had a relatively primitive exterior layer. If it was differentiated, maybe that was radiogenically driven and it differentiated from inside.
Yeah, but you're going to be driving off, in the impactor especially, you're going to be driving off your volatiles and making it very hot. So you're going to be essentially turning, what you're going to get is the refractory portion. So just a thought.
I mean, my honest take on this is that neither of these scenarios is going to be overwhelmingly, this is absolutely it. We're going to end up with capture is difficult, and I think an impact is going to end up having its challenges too, notably in explaining the spectra. And we're going to have to evaluate those side by side, hopefully with new data to better constrain it, to decide what we think is more probable.
Well, and I'll also throw in an advertisement for your...
Sorry, because we're running out of time.
Okay.